Dear students, I welcome you for the today's lecture related to the nozzles attached to the process equipments. This is in general any sort of the equipment that is attached with the nozzles. Basically, these nozzles we are going to discuss what are the nozzles, where they are used, then the selection of nozzle location, then the types of nozzles, then when you are taking out some material from the basic sheet, then what is the reinforcement that is required, then types of the reinforcement and designing for this reinforcement, that we are going to discuss. So these vessels, all the vessels, they are attached with the some or the other different attachments, and all these attachments that is provided with the help of the nozzles. So nozzles become the part of integral part of a vessel. Any vessel, it's a pressure vessel, any sort of the vessel. A pressure vessel is a closed container designed to hold the gases or liquids at a pressure from different ambient pressures. So if you will look at this figure, the different nozzles, they are attached and with the different diameters. Even in case of our pressure cooker, the nozzles, they are attached for the either for the safety valve or for the vessel. Here also in this heat exchanger, the nozzles or manholes, they are provided, and they are nothing but these simple pipes. Mostly it is the simple pipes which are available, and they are welded to the vessel. So nozzle is a device used to control the direction or characteristics of a fluid flow, as it exists an enclosed head or enclosure. So it is a part and parcel of a vessel for providing the flow fluid movement. So nozzles are used for inlet and outlet of your process material, for heating and cooling mediums, for drainage, for safety valves, and for rupture disc. All these are the different purpose of the nozzle, and their nozzles, they are attached at the different locations depending on its purpose. They can be either circular or elliptical in shape. Then these nozzles are tubes or pipes for with varying diameter. So they can be of a desired diameter attached to the vessel for its inlet, outlet, then hot and cold fluid utilities, that means your heating and cooling systems, even in case of manways or hand holes, then connections for safety devices like relief valve, rupture disc, then again for instrumentation and for measuring pressure gauge, pressure level, temperature, then sample points, then drains and vents, and they're located at any point depending on their use, except on weld lines. So whenever there is a welding, people try to avoid the attachment of the nozzles. So nozzles, they can be flanged or without flange depending on the type of attachment. More number of nozzles incorporate the more cost. That is, then the different types of the nozzles: integral nozzle, foam nozzle, fabricated nozzle. These are the three different types of the nozzles which is available. The integral nozzle, foam nozzles and the fabricated nozzles. So integral nozzles, they are nothing but are available directly on the vessel. As the name indicates, it is an integral part of a shell or the head. Now, if you will look at this plate, consider this as a plate, and I am having a hole in that. That is nothing but a hole nozzle. So it will be a part and parcel of that plate. That means a shell or a head. So that is what it is called a integral nozzle. It is the portion of the head or shell by cutting and shaping is given in the contour of the nozzle. That means I am going to cut the plate and give the shape of a nozzle. The material should have the good ductility for this purpose. Then taking the connecting parts of the nozzle and shells as the integral forgings, at the same time thickening, then the welding them with the nozzle and shells. The next is the foam nozzles. So foam nozzles forming with the specific purpose, that is whether it's rolling or forging, and are welded to the shell or the head. These foam nozzles are formed to the specific shape and size either by rolling or forging. Even in case of the casting, these nozzles, they can be formed. These are fabricated according to the temperature, pressure and the process requirement. These are formed to the specific shape and size either by rolling, forging, and are welded to the shell or head. That means we are not directly attaching the available pipe. That is main difference in a foam nozzle and a fabricated nozzle. We are specifically designing this. We are not directly using the available pipes. Then next is fabricated nozzles. These are the most commonly used in our chemical process equipments. These are the short pipes, pieces of pipes. That is the major difference between the foam nozzle and the fabricated nozzle. Fabricated nozzles, they are basically the pipes. These are the short pieces of the pipes or tubes, or fabricated from metal sheets and are welded to the shell or head wall at the opening made in the wall. So length of the nozzle is 1 to 2 times the diameter of the nozzle. Generally the one length of the nozzle is 1 to 2 times the diameter of the nozzle, and all these are your fabricated nozzles. Then the selection of nozzle on their location. So depending on the purpose or the utility of that fitting attachment, their location is selected. So the stresses around a nozzle located in a cylindrical shell are not the same in all directions. Ultimately, we are going to do the stress calculation. So how that nozzle that is attached to a vessel, depending on that, the stresses developed will be going to vary. So nozzles present on the peak of a dish end at do not disturb the symmetry of the vessel, but present on the periphery of a pressure vessel disturbs the symmetry, result in eccentricity, which causes the stress concentration around the opening. That means the vessel which will be available, if it is top head is available and I am putting a nozzle at the center, then it is not going to disturb its eccentricity. However, if I am going to attach a nozzle to one side, then the balance will get disturbed and this is going to develop the stress concentration. On this surface, the stresses will be more as compared to on this surface. So the attachment of different nozzles or the different pipes to a vessel, that disturbs the eccentricity. It is not eccentric in all directions. So as it is not eccentric, so there is a disturbance and which causes the uneven stresses, and these uneven stresses in the vessel may lead to the failure. So while designing the or providing the nozzles, one has to think about the symmetricity also. Generally prefer the nozzles with the symmetricity. Then a cylindrical shell circumferential stresses is 2 times the longitudinal stresses that we have already seen. The nozzle that cuts more material in the longer direction has the higher stresses. So if look at this figure, so this is the CFD, computational fluid dynamics analysis of the stresses. Now the two nozzles, one is in the longitudinal direction and one is in the axial direction, circumferential direction. So in this case, the red portion that is going to provide the stress concentration, more stresses will be observed in this red area. Then the nozzles with reinforcement plate. Basically, the material that is cut for the nozzles is going to reduce the strength of a metal sheet. So as I am going to make a hole into the vessel wall, so it is going to have the reduced strength for this wall. This wall will be reduced in strength as I am going to cut the material from here. So to maintain the strength of this cut portion, I am again going to provide the extra material over that, and that is nothing but it is called a reinforcement. So if you will look at this, the extra plate that is welded here to the basic metal sheet, that is called a reinforcement. Again here also the extra metal sheet that is provided in addition to the original metal sheet, so that is called a reinforcement. This is the area of the vessel wall removed is compensated by using the additional material in the form of this metal sheet. That means whatever the area that is removed, the same amount of the area that is to be provided. Area of the metal sheet that is removed. So same amount of the metal sheet that is to be provided, and that is why we are going to weld the additional metal sheet around this nozzle to increase the strength of the original metal or the vessel. So when the hole that is drilled in a vessel wall, uh, the much portion of the vessel becomes weak. So the area of the vessel wall removed is compensated by using the additional material in the form of a metal sheet. The stress concentration in the vicinity of nozzle can be reduced by providing the extra thickness to the vessel wall or the nozzle. So this stress concentration can also be reduced by providing the additional plate to the vessel wall or to the nozzle, and it is called the reinforcement plate around the nozzle. So to avoid the failure in the opening area, the compensation or reinforcement that is provided. So care to be taken as this additional compensation do not disturb the strength pattern existing in the vessel wall. That care has to be taken so that the stress developed into the vessel that should not be disturbed. Then the reinforcement nozzle having the wall thickness larger has the minimum stress concentration in that area. Then reasons for stress concentration: material of the vessel wall is deteriorate and the continuity of the structure that is damaged. Now it is in this figure you can see the this is the vessel shell, original vessel that is available. This is the original vessel which is available, and this portion that is removed from this to this side, that portion is removed, and there we are provided with the nozzle, and here we are provided with the nozzle. So the available area which is compensated, that is the reinforcing pad or the reinforcing plate that is used. In this figure you can see the nozzle attached is up to the wall vessel shell thickness. Inside diameter of the vessel shell and the inside diameter of the nozzle, they are same. Now coming to the second figure, this is the vessel shell, this is the reinforcement pad, and this is your nozzle. So this is extended inside the vessel also. There is a possibility that I can extend this nozzle inside the vessel. That is the another case. One case, the up to the shell only I am going to provide the nozzle, and in second case I am going to provide the nozzle which is protruding inside the vessel. This is protruding inside the vessel. This part of the nozzle is going inside the vessel as it is shown in this figure. Now here the balanced compensation and unbalanced compensation that is there. The balanced compensation, the compensating material or the plate is provided on both the sides of the vessel wall. That means in this figure I have provided the compensating ring only on the one side of the vessel. I can provide the compensating ring, this is the reinforcing pad or the compensating ring, on the inside of the vessel also, on both the sides. So this is already provided and this is additional provided, that is it is balanced on both the side, inside as well as the outside. That means the reinforcing pads, they are welded on the outside as well as the inside of the vessel shell. That is the balanced reinforcement. And in case of a unbalanced compensation, the compensating material or the plate is provided either on inside or on outside of the vessel wall as shown in this figure. The compensating plate or the reinforcing pad that is only provided on the outer surface of the shell. In this figure also, this compensating plate that is shown on the outer surface, you cannot see the inside surface, but generally it is the unbalanced compensation that is provided. Mostly it is the outside welding that is provided, it is because of the ease of operation. Then the pad reinforcement significantly reduce the both the tangential and radial stress says on the vessel and in the nozzle region. This is what the unbalanced compensation, that is the integrally reinforced vessels means one piece forged nozzle. Okay, now there is how to design for this compensation. The designing of a compensation that is done by area for area method. The area of a plate or a shell which is removed, the same amount has to be provided. Now look at this figure. That is, this is the shell part which is provided, and in this shell part the nozzle that is attached. Here the nozzle that is attached. So I am going to do the calculations associated for this area for area method. That is, the maximum horizontal distance is KL. This is the K and this is the L. This is the maximum horizontal distance, should be 2 times the nozzle diameter. 2 times the nozzle diameter. That is the self compensation limit. The maximum horizontal distance limit is twice the diameter of the nozzle. This is one of the requirements for self compensation. Then second requirement for the self compensation limit is the maximum vertical distance. Maximum vertical distance that is associated with the km. This is again the k and m is this. So it is the length of a nozzle pipe that will be taken into account, km, and that should be the 6 times the thickness of a shell. 6 times the theoretical thickness of a shell, or the 3.5 times the thickness of a shell plus 2.5 times the thickness of a nozzle. Rs is for the shell and Rn that is for the nozzle. N is for the nozzle, S is for the shell. So theoretical thickness of a shell based on the external pressure only that is calculated without considering the corrosion or the excess thickness. Then the required compensation of nozzle is nozzle to be related at the maximum allowable working pressure. For that we have to first theoretically consider or calculate the theoretical requirement of a shell, thickness of a shell, theoretical thickness of a nozzle. That is what is basically actually required. But in actual practice, we add the corrosion, we try to get the maximum round off values. We also design the excess. So excess designing, round off, and the corrosion allows. that is the extra addition which we do in the calculation of a thickness. So here it is the theoretical thickness calculation of a shell, and that is calculated as PD upon 2Fj, that is the pressure, diameter and the 2Fj. So here ds is the diameter of the shell. Then similarly, the theoretical calculated thickness of a nozzle, that is also PdN upon 2Fj plus P. This is the theoretical requirement. Ts, that is the actual thickness of a nozzle that is used. Here I have used the actual thickness of a nozzle. That is the Ts is the actual thickness of a nozzle. Then Tc is the thickness of the corrosion allowance. Ts1, that is the thickness of a nozzle without corrosion allowance. So Ts1, the thickness of a nozzle without corrosion allowance, which is equal to the Ts actual thickness of a nozzle minus the theoretical thickness of a nozzle minus the corrosion allowance Tc. Similarly, Tn1, that is the nozzle itself, that is in excess, the thickness of a nozzle in excess, that is Tn is the actual thickness of nozzle minus Trn, that is the theoretically calculated thickness of a nozzle minus Tc, the corrosion allowance that is provided. And the area for the nozzle, that is pi dn into the t, diameter of the nozzle into the thickness. This is what the actual area of the nozzle that has been taken out, pi d into the thickness. So the thickness is provided in excess while fabrication is given by. Now the required compensation for nozzle to be rated at the maximum allowable working pressure P of a shell pressure head, that is the AR, which is equal to the dn, diameter of the nozzle, minus 2 times the thickness of a nozzle. This is the actual area that is to be required. Now here this is what the area that is removed from this plate. This plate I have removed this area, right? And I'm going to provide a nozzle in that. Now here I am going to provide a nozzle in that. So nozzle itself is having a certain thickness. So this is what the nozzle thickness I am going to provide it. So there is a difference in the diameter. Actual nozzle diameter is this, but the actual diameter of the plate which is cut is this. That is the cut diameter is different, and the nozzle diameter is different, and the thickness, which is the plate thickness. So this much amount of the area that is removed. The area available for the compensation, one is from the metal thickness available with the shell or the head, and nozzle itself is having the excess area, the portion of a nozzle inside the shell. This is external to the shell, inside to the shell and external to the shell. This is generally we are seeing the external to the shell and the inside to the shell. That is, it is protruded inside the vessel. This is the inside the vessel. This is external to the vessel. So the portion of the nozzle inside the shell or head and the portion of the nozzle external to the shell or the head. So area, this much area that is removed. Out of this area, some area which is already in excess with the metal sheet thickness, because we are taking here the round off, we are taking here the corrosion allowance, we are taking here the excess also. Theoretically excess required 1.1 times. So this is the extra area that is available in this plate. तो वो प्लेट में ऑलरेडी कुछ तो थिकनेस अवेलेबल है. Then this nozzle itself acts as a reinforcement, one which is outside the vessel and one which is inside the vessel. That is what the reinforcement provided by the nozzle, reinforcement provided by the metal shell thickness, and that is why we are taking out the three areas directly. So total area removed minus the excess metal which is available with the shell, excess metal which is available with the due to the nozzle in outside the shell, and the external thickness which is available out due to the inside of the nozzle. So these three nozzles, they are already these three areas which are already available. This compensation is provided by compensation ring which is welded to the periphery of the shell. So once we have calculated the compensation area, and depending on this compensation area, we are going to provide these reinforcement plates, either welding on the outside or welding on inside or on both the sides of the vessel shell. Now, if the vessels they are not designed properly and the nozzles they are not uh, properly allocated, then there may be the hazards that can also occur inside the vessel. Now here the so many looking at this figure, there are so many number of nozzles which are provided in this small area, and this had weakened the basic shell, and because of the weak shell, and if it is under the vacuum, this is what the shrinking of the vessel because of the vacuum that caused this uh, to squeeze it like this. Similarly, you can have such an accidents, or here the third figure that is also there. Here also you can see the nozzle that can get damaged if the compensation is not provided properly, reinforcement if it is not provided properly. So this is all related